Lecture 1.1, what is thermodynamics? So in order to answer this question, we really are asking this question. How do materials change while undergoing a thermodynamic process? So it's all about how does a material change. So when you read thermodynamics, the word dynamic is understanding how heat energy transfers. And sometimes people say, how does heat energy flow from one object to another? But most of the time, we're not interested in how it flows from one object to another. What we really say is between the system and the environment. So dynamic is understanding how energy transfers from one object to another or between a system and the environment. And to give you a sense of what this means here, let me give you an analogy. And what I'm going to ask here is that how does heat affect the states of an egg? Well, it depends on how you're going to heat that, because the outcomes can be quite different. You could have a soft versus hard boiled egg, or you can have a scramble. That's a different process of transferring heat. Or you can have an easy over, or the countless other variations. But how you transfer heat to the egg really changes the structure of the egg. So in thermodynamics, there are two different viewpoints. Yeah, there are two different viewpoints. One of the viewpoints here is what we call classical thermodynamics. And when we talk about classical, we talk about a macroscopic viewpoint. And when you look at classical, this is really, it's experimental evidence that drives its postulates. But there is a different one, which is statistical thermodynamics, and this comes from a microscopic viewpoint. And then here we calculate properties starting from molecular models or atomic models. And it turns out that in this course, we're going to use both of those again and again and again, simultaneously. Now, since thermodynamics is about the flow/transfer of energies, we need to talk about work and energy viewed from introductory mechanics. And here at Cabrillo, this is called Physics 4A. So in this course, one studies energy transfer of macroscopic objects. And as an example here, we could imagine that we have a sliding block on some path. So in other words, maybe I have a system that looks something like this, where now I have a block right here that has a certain amount of energy. And as it has a certain amount of energy, it starts off with some kinetic energy. And as it moves through this environment, it gives you, we can look at this from an energy viewpoint. And what we know here is that we know that kinetic energy is not a conserved quantity. Because if I look at, let's say, point 1 here versus point 2 here, and then point 3 here, at each of these places, the kinetic energy will be different. And another thing that we learned here is that potential energy is not a conserved quantity of nature. And again, if I look at points 1, 2, and 3, they each have different potential energies. However, if the block is isolated, now this turns out to be a really important piece. If it's isolated, then what I can do here, so I'm going to, in fact, because this is so important, I'm actually going to color that. If it's an isolated system from the environment, the total mechanic energy is conserved. And what that really means here is that if I have the kinetic energy plus the potential energy, this is a fundamental constant of nature, and this is what we call mechanical energy. And again, what we say here is that the key point is it is isolated. Isolated from the environment. But there's a problem. Most macroscopic objects are not isolated. And one example would be if you look at friction. If you include friction, that environment, that changes the mechanical energy. And the work energy theorem must be applied. So the way we handle this is we then say that the network, which is equal now to the change in the mechanical energy, really reads that if I start off with some macro energy 1 and I do some work, this here changes the energy of the system. And so what's really, really important here is that this work, what it does here, it's a transformation process. That's what work really does. It's a transformation process that changes the energy. It changes the mechanical energy here. But unfortunately, this definition of the work energy is incomplete and must be required. This work energy theorem is incomplete and requires modification to include thermal processes. So let me give you an example. And let's say that you're going to boil water in a pot. Clearly, if you're going to boil water in a pot, you surely do not want this pot of water moving. So the question is this: what does the work energy theorem say about this? Well, you could imagine that I have this situation. I'm going to have some type of heater, like on a stove, right? Here's going to be my hot part of the stove. And so when I'm looking at this thing, we could see here is that this is going to be the stove. And then on top of this, I'm going to put a pot and then I'm going to add some water here, which we are now going to boil. And as you boil it, of course, you're going to create some water vapor above. So here's my pot here. So if I'm looking at this pot, what the work energy theorem says is that it says this here. that if there is no macroscopic energy, then that implies that the work, the net work done, has to be equal to 0. So once again, why do we not, when I say no macroscopic energy, that means that we do not want to move or lift the pot. That would be silly. So according to the work energy theorem then, this tells us then that then if the mechanical energy remains 0, then that means the macrokinetic energy and the macro potential energy have to be 0. However, there is clearly energy transfer from the stove to the pot. So what this implies here is that the environment plays a significant role, which then means again that this is not an isolated system. So what we conclude here that the work energy theorem from mechanics is incomplete. And therefore, we have to modify it. So here we go. So the way we'll do this here is that we'll start to look at it in the following way. That to include heat into the work energy theorem, we must look at the microscopic energies too. So in summary, here's what we can say. One, if we have for an isolated system, from the environment, what we say here is that the network of the environment, that is 0. And as a consequence, that means the change in mechanical energy is 0, and that leads to the change in the macro kinetic energy and the change in the macro potential energy. This statement leads to conservation of mechanical energy. By definition, this is the conservation of mechanical energy. Two, for a system that includes the environment, there are two transformative processes that change energy. So one of them we've already talked about, that's what we call working. And that means that there is a network that's not zero. That will change the energy of the system. Now we said here that there's a second kind, which we now call heating. And when we look at heating, we define heat by the symbol Q. And this heat is not zero. And what we say here is that heat is the workless transfer of energy. So in other words, working and heating are on the same footing. They do the same type of thing by changing energy here. So if we include heating into the work energy theorem, here's what we find. We find that the network plus the net heat going in or out of the system not only changes the macro energy states, but it also changes the micro energy states, where we see that E macro is the same as K macro plus U macro, whereas E micro is the same as K micro plus U micro. But we could modify this work energy theorem even more so. So referencing the boiling pot of water, we do not want this pot to move macroscopically. For safety reasons. As a consequence, so this implies immediately that then those macro energy states are zero. So we can then rewrite the work energy theorem. And it's when we rewrite this thing This is what they call the first law of thermodynamics. And the way it now reads here is it reads like this. It says that the net work plus the net heat now is going to change the micro energy states, but we typically don't call them the micro energy states. We call it the internal energy. These are all of the energies internal to the system. And we will then abbreviate this like this here. So the work energy theorem, or the first law of thermodynamics, is just the work energy theorem where we include micro energy states, where E internal is the same as E micro, which is the same as K micro plus U micro. Okay, I'm all the way at the edge, so I'm going to move these over. So if I had to draw a picture of this thing, so picture-wise, the total internal energy is the total microscopic energies. Within the system. So I could imagine that I have some system. It could be a baseball. It could be a pot of water, but I have some system. And so what I'm seeing here is that within this system, what I'm going to have here is that I'm going to have a connection between particles that look something like this here. And what connects all these particles, we could imagine that there's like little springs that connect all of these guys. So then what you're seeing here is that the springs represent electrical bonding. And this then tells us about the micropotential energy. But each of these little molecules can be moving in different directions. So all of a sudden, I could then represent these guys by kinetic energies, and I can represent them by potential energies. So what you're seeing here is that when I write U micro, it's going to be the sum of all of these little microscopic potential energies, and then K micro is then going to be the sum of all of these individual kinetic energies. In many textbooks, the internal energy is called the thermal energy. I will not call this E thermal. I will only call it internal energy, and that's the same language that people use in more advanced courses. So the first law of thermo sets up the framework to understand and analyze all thermal questions and problems. So this is the scaffolding that we will use.